Yeah, that too.
So if you allow me to use this notation, I don't know what the best notation is, but this is KE magnitude square. I think some textbook would just call this KE square. KE square, but this is a scalar number. Okay, maybe if you have the understanding that this is KE square, that's fine. There's no complex conjugation here. Okay, sometimes you put the magnitude sign, it means complex conjugation. But there's no complex conjugation. This is KE dot KE. This is a scalar number times E, which is again a scalar number, is equal to omega square mu square H square, which is again a scalar number. So we have this condition that this scalar number square, or maybe I should put this scalar number square over this scalar number square is equal to omega square mu square, but KE dot KE would be just equal to kappa square, which is just this one over here. So omega square mu epsilon. So this is precisely equal to mu over epsilon. Okay, so you see that irrespective of what EI, HI are, as long as they are equal to each other, if you are in a homogeneous medium, the ratio of the magnitude of the E field to the H field is always equal to that. That is just the impedance condition. This is the impedance of free space. If you would allow me to say this is just E magnitude over H magnitude is equal to mu epsilon. But be careful, this magnitude is defined without the complex conjugation. Okay, just E dot E, square root of. So you see a kind of a perfect matching, even if you have EI and HI being different from one. Okay, and they can be complex numbers as well, as long as they're equal to each other. Okay, so let's look at this coordinate stretching modified Maxwell's equation for the single interface problem.
So excuse me about
Yes?
the final line, because I think if we multiply the original equation by its conjugate, then it will result in what you get, right? But also the mu should get absolute value.
Right. You put the complex conjugation here. Things are not that clear. If you put complex conjugation here, you have to keep the complex conjugation on KE. I assume that my E and H can be complex numbers. Okay, so this will have to be complex conjugated. One of these has to be complex conjugated. This will be kappa E square, but this relationship wouldn't hold anymore. This relationship wouldn't hold if one of them is complex conjugated. So I cannot use complex conjugation to derive this, because this relationship holds true when both of these are not complex conjugated. And EI and HI can be complex numbers. Okay?
Does that mean it's not positive definite?
What is not positive definite?
I thought the conjugation of one of them was to ensure that it was a positive definite when you have complex.
That's right. This is not going to be a positive definite number. This is not going to be a positive definite number. It can be a complex number. It's a scalar. That's what it means when you do an inner product without complex conjugation.
Oh, so it can be complex.
Right.
Should we add the absolute value on both sides, because we take absolute value on the left-hand side?
Yeah, I hate to put an absolute value over here, because absolute value often means complex conjugation. Okay? So even if I put an absolute value here, I should have a warning sign saying that there's no complex conjugation when I multiply the two things together. Okay, it's a dot product without complex conjugation. So this absolute thing has a different meaning. Okay? It's not the mathematical absolute value. It's just that you take two numbers, two vectors which are complex vectors, dot multiply them and taking the square root, you still get a scalar number. Okay? So let's look at a single interface problem. Single interface problem. And let's look at the TE to Z case, where we assume that we have a single interface, and then there's this Z-axis, and then there's this plane wave coming in, but the E field is such that it's transferred to Z. So the incident field is of the form of E naught, e to the ik incident vector, this is ki, dot r. And E naught is transverse to Z. So this is a TE wave. I just demand that my E naught be transverse to Z in that manner. And that I know that KH, actually KH and KE are the same in this thing. This follows from the divergence of H dot E equal to 0 condition. Okay. So for the K vector that corresponds to the incident wave, this must be true. And then I will have a reflected wave. The reflected wave must come up with the K vector KR. And you can write the reflected wave as in ER is equal to RTE E naught e to the I KR dot R. Okay, so there's a reflected wave for the single interface problem. And then there will be a transmitted wave, which I say have a vector KT. And then the transmitted wave will have a form ET is equal to T, TE, E naught. T. Let me assume that these are not the same to begin with, and prove that actually they have to be the same. So the transmitted wave is something of this form, and assume that E naught R and E naught T are not the same as E naught to begin with, but let me assume that they have to be the same finally. Okay. Otherwise, you cannot match boundary condition. Okay, E naught T has to be equal to E naught R has to be equal to E naught T. Otherwise, it's not possible to match the boundary condition. Then, because of that, you need only to match the tangential E continuous boundary condition. And then you need phase matching. You need phase matching, it means that KIX must be equal to KRX must be equal to KTX. They all must be equal for phase matching to be the same, and then KIY must be equal to KRY must be equal to KTY. Okay? And then these three quantities must be the same in order for you to match boundary condition for tangential E continuous. Otherwise, it's not possible to match tangential E continuous. Okay? And if you mesh tangential E continuous, then you have this as one of the equations, TTE. Okay. And then the other boundary condition should be that tangential H is continuous. So you like to find tangential H. If you remember, in order to find tangential H, you say KE cross E is equal to omega mu H. In this new system of equations that we have, KE cross E is omega mu H. So if you use this condition, we can derive a tangential H boundary condition. And if I call this region 1 and this region 2, then I have H1. The field in region 1 must be equal to KIE cross E naught over omega mu 1 e to the I KI dot R. Okay, that is the first term, which is this first term over here. The magnetic field that corresponds to the first term. And then the second term, which is the reflected term, I find the corresponding magnetic field will be KRE cross E naught over omega mu 2 e to the I KR dot R. That is the one that corresponds to that term, and then I have H2. The field in region 2 should be TTE, KTE cross E naught over omega, sorry, this should be mu 1, mu 2 e to the I KT dot R. And now if I demand that the tangential component be equal, this is E naught is completely transverse. E naught is transverse to Z. So the only thing that will produce the tangential component from here is the Z component of this crossing with this. The X and Y component of this crossing with this will produce a Z component. If I want to look at the tangential component of this, it will be the Z component of this crossing with that. Okay. And then similarly, it will be the Z component of this crossing with that. Okay. And then if you take into account of that, then finally what you have is that and then because of this condition, you have KIZ is equal to KRZ. Okay, KIZ has to be equal to KRZ because of this phase matching condition. Actually minus, right? Minus. Because this have to be opposite in sign to each other if you look at this picture. And so if you take into account that the Z component of this is negative of that component of that, you will finally end up with this equation. I'll just write down the equation, okay? I can explain to you why it becomes like that. It's equal to T, TE, K2Z, E1Z, mu1. Okay. Because KIE is proportional to z component k I z over e I z. Okay, because of coordinate stretching, there's an e I z in the denominator. So if you take this and multiply across, okay, take the k2z, e2z from it and multiply across, you get e2, and then take this mu2 multiply across, you get mu2 here. So this is the equation that you finally get. Okay? Is everything okay so far? Take the z component of it, cross it with that, and then you will have this thing equal to that, and then there's a mu1 in the denominator, mu2 in the denominator. The cross multiply to give you the. In the case of no coordinate stretching, this E1z and E2z will not be there. Just think of the case where there's no coordinate stretching. So the only difference is that it's E1z and E2z. And then this is the same as the case without coordinate stretching. So coordinate stretching, just bring in this two new variable into your equation for the reflection and the singular interface. And that variable makes a big difference. You see that the stretching in the z direction is very important now for this single interface problem. You can take a 5 minutes coffee break and come back and look at what coordinate stretching does to the single interface reflection problem. Especially if you allow this E1z and E2z to be complex numbers. Okay, you take a break. I think I have some home homework here.